Hello everyone, my name is Neel Kundu and welcome to my poster presentation titled MIMO Terahertz Continuous Variable Quantum Key Distribution. In this work, we have proposed a multiple input, multiple output transmission scheme for wireless continuous variable QKD protocol operating at terahertz frequency for future 60 wireless communication networks. As compared to the optical frequencies, which are generally used for implementing QKD protocol, terahertz frequency offer a number of advantages. For example, terahertz can support mobility as it requires less delicate pointing and tracking of the receiver. Moreover, terahertz is less affected by ambient light, clouds, and dust. Furthermore, as compared to the lower RF microwave frequency, terahertz frequency has lower preparation thermal noise. Therefore, it can support positive key rates at room temperature. However, the atmospheric absorption loss and the path loss at terahertz frequencies are quite high, which leads to lower secret key rates, and the maximum transmission distances are also limited. In order to overcome these challenges, we have proposed a multiple antenna transmission scheme for Terahertz CVQKD as shown in this figure. So this MIMO technology is a mature technology in classical wireless communication, and it has been used in various 4G and 5G cellular systems and has also been standardized in Wi-Fi technology, which we are using regularly. However, the potential of MIMO transmission for quantum communication has not been fully investigated in quantum communication regime. To the best of our knowledge, this is the first work that proposes a MIMO transmission scheme for continuous variable QKD. So the schematic of the MIMO CVQKD scheme is shown in this figure, where Alice and Bob have multiple transmit and receive antennas. First, the wireless MIMO channel between Alice and Bob is estimated, where Alice transmits known pilot signals to Bob. Then Bob measures the received signals and then uses our least square based estimation scheme to estimate the channel matrix as given by equation 2. And after estimating the channel, this is fed back to Alice by using the classical authenticated channel, which is also required for classical post-processing in the QKD protocol. After the channel has been estimated and is known at Alice and Bob, they use a singular value decomposition based transmit beamforming and receive combining as shown in this figure. Here, Alice used the matrix B to first multiply the input modes, and Bob uses the combining matrix U dagger to receive the modes. After this beamforming and combining, the MIMO channel between Alice and Bob is decomposed into parallel single input, single output lossy Gaussian channels, whose input-output relation is given by this expression. And here, this Ti is the ith non-zero eigenvalue of H Hermitian H, and it denotes the transmissivity of the ith parallel single input, single output channel. And there are additional noises due to detector noise and the channel estimation errors. So in this work, we have theoretically characterized the achievable secret key rate for two types of attacks. First is the individual attack, which is a weaker attack, and the other is the collective attack, which is the strongest Gaussian collective attack. So for both, we have incorporated the effect of pilot length, which is given by TP. And here TC is the coherence time of the channel over which the MIMO channel remains constant. We have also incorporated the effect of imperfect reconciliation arising from this parameter beta, modeled by this parameter beta. And we have also incorporated the effect of detector noise due to homodyne and heterodyne detection and the channel estimation error noise. So here we see that the secret key rate is the sum of the secret key rate of R parallel single input, single output channel. Here R is the rank of the MIMO channel H, which gives the multiplexing gain of the MIMO scheme as compared to single input, single output scheme. Moreover, the channel transmittance of each of these parallel size of channel is increased due to the coherent beamforming and combining used by Alice and Bob. Therefore, this gives a power gain which increases the secret key rate of the total system as compared to the baseline single input, single output system. Now here we compare the achievable secret key rates for both types of individual and collective attacks using homodyne and heterodyne detection scheme. These are the practically achievable key rates, and we also compare with the upper bounds. So in the upper bound expression, they assume that the perfect channel knowledge is available and there is no detector noise at the receiver. So first we observe that the secret key rate obtained from homodyne and heterodyne detection scheme are almost the same because the detector noise is increased in the heterodyne detection scheme as compared to homodyne detection scheme. Furthermore, we see that the secret key rate, which is practically achievable, can be significantly reduced at large transmission distance as the gap between the upper bound and the achievable rate decreases. This decrease is due to at large transmission distance, the channel estimation error increases, and this leads to a rapid reduction in the achievable key rates. Furthermore, if Eve has the resources to implement a stronger collective attack, then the secret key rate can be significantly reduced, as shown in this plot for both 32 by 32 and 256 by 256 MIMO architectures. So in conclusion, we have proposed our MIMO transmission scheme for Terahertz CVQKD system, which can be used for unconditional security in future 60 wireless networks. We have proposed a channel estimation scheme, which is necessary for implementing the singular value decomposition based beamforming and combining. And we have incorporated the effect of pilot overhead, the channel estimation error, and the detection noise in our secret key rate analysis. And we have carried out a feasibility study of Terahertz CVQKD using numerical simulations. We believe that by the time practical quantum computers pose a real threat to the current RSA encryption scheme, which may be in the next 5 to 10 years when large-scale quantum computers are available, by that time, terahertz signal generation, detection, and antenna technology of terahertz frequency will be mature enough to practically realize this MIMO terahertz CVQKD system, which we have proposed and can be used for 60 wireless networks. And the quantum secure keys which are obtained from this protocol can be used for one-time pad-based physical layer security or for symmetric key encryption algorithms. Furthermore, the quantum secure keys can be used for seeded post-quantum encryption algorithms for 6G security in the 2030 and beyond. Thank you for your time.